Guten Tag, Berlin! Ich bin Dave Aronson, der T-Rex von Kodosaurus, und ich flog her auf meinem Pterodactylus, euch ACRUMEN zu zeigen, meine Definition von Softwarequalität. Jedoch auf Englisch. So I'll be telling you my definition of software quality, but why? I think a lot of us would agree that the state of software quality these days is pretty poor, and I think one of the reasons why is the lack of an agreed upon definition. If we don't have a definition, it's very hard to achieve, and if we don't share that definition with someone else, then it's hard to convince them that we have achieved it when we at least think we have. So I'm trying to get everybody on more or less the same page. Yeah, I know, good luck with that. But before we dive in, I'd like to level set some expectations. This is not really meant for the extreme levels of quality associated with things like avionics, implanted medical devices, nuclear power plants, or even banks or telephone switches. It's meant for the other 5 nines of us, writing typical consumer-grade web apps and mobile apps, things like that, maybe business apps in some less quality-critical industries, where if something goes wrong, there may be frustration on the user's part and embarrassment on ours, but nobody's going to die or even lose a lot of money. Those other kinds of industries usually have their own approaches, including lots of regulations and much closer inspection than our software is likely to ever get. So with all those examples around of ways to produce really high quality, why do we need a new definition? Well, several years ago, I was looking for a good general definition, but everything I found had some very serious problems. Most of them were long lists of complicated terms, full of developer jargon. Now, jargon is fine when we're talking amongst ourselves, but I wanted something other people would understand, even non-technical people, so they could understand better our challenges and give us more precise feedback on exactly how our software sucks. And you know most of it does, right? Some definitions were proprietary, forcing us to buy very expensive software tools, or at least relatively expensive documents. Some were only applicable in the context of certain technologies, often also proprietary, or certain styles of programming, most notably object-oriented. But I wanted something more flexible that we could use with all software and for free. Some of them were only about issues of concern to us developers, ignoring the needs of the users and the many other categories of stakeholders. Some weren't even about the software at all, but about the process and its byproducts, saying that we have to hold these meetings or write those documents. Oh, some of these meetings and documents may be helpful, but to make them the definition, I felt completely missed the point. I wanted something more focused on the software and descriptive, not prescriptive. So long story short, but maybe too late for that, I didn't see anything that I liked, nor that was commonly accepted. So in the spirit of XKCD, I decided to make my own. But rather than take the usual approach of incorporating the best parts of all of the existing approaches, I tried to pare it down to just the bare essentials. And I wound up with a list of 6 aspects with simple names and relatively simple explanations. The whole thing is so short that it literally fits on the back of my business card without even using fine print. See me afterwards if you want one as a cheat sheet. I call this list of aspects ACRUMEN. Now, that's a Latin word meaning sour fruit, such as lemons, which is why you'll see a lot of bright yellow, lemon yellow in these slides. It's the official color of ACRUMEN. So what does ACRUMEN mean in this context? The acronym ACRUMEN, try saying that 10 times fast, just takes those 6 aspects and puts them in priority order. So by now, I'm guessing some of you are wondering, what are those blankety blank aspects already? That's the real meat of the talk. They are that software should be appropriate, correct, robust, usable, maintainable, and efficient. Now, that might not be immediately obvious what quite all of that means, so let's unpack it a little more. First and foremost, software should be doing what the stakeholders need it to do. In other words, do the right job. Actually, more likely the right jobs, because you might notice I said stakeholders, not just users. There are many, many others, just starting with the people involved in the development, deployment, monitoring, customer service, and on and on and on. Now that we've identified those jobs, it needs to be doing those jobs without bugs or other errors. In other words, doing the job or jobs right. So correctness is pretty much what it sounds like. It should be difficult for anyone to make the software crash or otherwise malfunction, whether deliberately or on purpose or by accident. And on the beam, we like to say let it crash, but I mean mostly a more permanent crash, and even the temporary crashes should not be readily visible to the users. On the other claw, it should be easy for the users to use and for the developers to change. The other way around, not so much. And last, dead last, despite how we developers tended to worship this just a few decades ago, and to some extent we still do on the beam because it's so great at this, it should go easy on resources. But not just the technical resources we usually think of, but some soft resources as well. Now, I've said there's 6 aspects, and you see 6 up there, but ACRUMEN has 7 letters. So what does the N stand for? Nothing. I just tacked it on to make a real word, even if an obsolete one. Now, while the basic definition is fresh in our minds, I'm going to answer a few frequently asked questions. First, other than going into detail on the tips how to achieve each aspect, how do we use ACRUMEN itself, just the list? Mainly, we can keep it in mind as sort of a checklist when writing or evaluating software. We can ask, is it appropriate, is it correct, and so forth? Or maybe how appropriate and correct and so forth is it, whether on a scale of 1 to 10 or just simple triage or what? Or is it good enough for our needs? And if it's ever not good enough, we can ask what can be done to make it so. In the short term, we can try to ensure that our current project will meet these criteria, and in the long term, that our processes will support these criteria with helpful activities and requirements, maybe even an explicit evaluation against the ACRUMEN aspects. We can also set targets for how good we need it to be in each aspect. And that leads us straight to the third most frequently asked question. After that, we'll backtrack to the second one. And that is, how can we boil this down to one number that will tell us the level of quality of a piece of software? Mostly I would advise, don't do that. Keep 6 numbers, 1 for each aspect. One number might tell us that a piece of software is overall kind of good or bad, but 6 numbers will tell us how. With a chart like this, we're probably looking at something that does most of what it needs to do with minimal extra bells and whistles, does it absolutely correctly, but not very efficiently, probably slowly. That would be impacting the usability. It's also fairly robust and maintainable, but could use some work there too. And these numbers can help prioritize further work on this system. Now we can backtrack to question number 2. Is ACRUMEN, or ACRUME without the meaningless N, always the right order? Some projects seem a little different. And the answer is no, that's just the typical case. Your mileage may well vary. You can consider, for instance, a company internal physics simulation tool that just needs to get a close enough answer, not something precisely correct, which might take forever to calculate precisely, like weather forecasting or something. It might not need to be so, it will need to be very appropriate and reasonably efficient. The correctness doesn't need to be quite so precise, so you could say that's a little deprioritized. It might not need to be so robust because of the limited interfaces and fewer things to go wrong. And usability, well, it's just for us, not for customers, so not so much on that. And maintainability, well, it's using a standard formula that's never going to change, so we're probably not going to have to maintain it much, so that is also deprioritized. So something like that might have a list more like this, ACRUME, rather than ACRUME. The only real constant is that appropriateness will always be at the top. And we'll see why now, because we're going to delve deeper into each aspect in turn, starting, of course, with appropriateness. If our software doesn't have this, then nothing else matters. If our software is doing the wrong job, it doesn't matter how well it's doing the wrong job. So appropriateness is not only more important than any one of the other aspects, it's actually more important than all of the rest of them put together. And yet, we developers are generally not taught that this is even a thing, let alone one that we need to be thinking about. And to prove this importance, let's try a little thought experiment. Suppose you want me to write for you a program to play checkers, or if you prefer British English, drafts. And I write for you the world's greatest chess playing program. It's as correct, robust, usable, maintainable, and efficient as anyone could ever possibly want. But are you going to be happy with it? Probably not. But why not if it's such a great program? Because it's not checkers. It's not what you asked for. It's not what you presumably need for various values of need. Or in ACRUMEN terms, it's not appropriate. There we go. So now that we know how important it is, how do we achieve it? In an ideal world, we would have frequent direct contact with the stakeholders of all types, ideally face-to-face or as close to that as we can get. But in this world, we generally don't get that. And second best would be to bring in the experts, which in this case would be requirements analysts. But on this planet, we don't usually get those either. So we'll usually have to settle for occasional indirect remote contact with representatives of some stakeholders. But even that is very helpful. Being able to contact somebody with some clue is very useful. And once we think we have some good grasp on their needs, we can show them mock-ups and prototypes of what we intend to do and demos of what we have done. And this gives them a chance to correct our wrong ideas about what they need before we go too far down the wrong rabbit hole. Has anybody been there? Wasting time implementing the wrong thing? Yeah, I'm seeing a bunch of hands and some nods and so on. So ideally, we show them these things frequently as a sort of continuous course correction. But there's one more thing that I'm going to return to over and over in this talk. We can propose tests. And in particular, for this purpose, I like the given, when, then format. Given these preconditions, when this happens, usually some kind of user input, then this is the result. Usually either something the user sees on the screen or the data is in a new desired state. This makes a great link between the worlds of business and tech because the business people can understand it, and we techies can turn it into a runnable test. Our next aspect is correctness. If our software doesn't have this, then it has bugs, and nobody likes that. Nothing can actually stop us from writing incorrect code, at least with the reasonably effective tools we have today. So the big question really is, how do we know? As you probably know, tests prove whether or not our software is correct, assuming, of course, that our tests are correct. But even then, that's not quite true, but I'll get to that in a moment. Ideally, our tests are automated, so they're more repeatable and maintainable and faster, so they give us feedback while the problem at hand is fresh in our minds. Again, assuming that our tests are reasonably efficient. We can start with the tests that the stakeholders just approved for the sake of appropriateness. These are likely to be high-level tests, like end-to-end system tests or feature tests, but we should still add our own low-level things like unit tests and integration tests and so forth. But even then, normal tests like these can only test the cases that we thought to test. But there are some advanced techniques that can help find the edge cases and such. For instance, property testing tests whether some desired property of our system holds true for all valid inputs. A property testing tool will make lots and lots of more or less random test data to try, similar to the security concept of fuzzing, except it's staying within defined bounds of validity rather than trying to find them and exceed them to see what happens. If we find an input that makes whatever property we've defined fail, then we know there's some edge case that we didn't consider. Mutation testing runs our tests against slightly changed versions of our code called mutants, and each mutant should make at least one test fail. If it doesn't, that means that we probably have a gap in our test suite or some redundant or unreachable code. Sometimes it's a false alarm, but usually it's something we should do something about. And by the way, I also speak on that at conferences such as CodeBeam Europe 2022. Anyway, we should have enough test coverage of assorted kinds and levels to have strong confidence in the correctness of our code. Next up, we have robustness. If our software doesn't have this, then at best, it might show a lot of error messages and seem fragile and unreliable. Or it might actually crash or malfunction and be fragile and unreliable. Or it might even get hacked because robustness includes security. The short explanation is that it's difficult for anyone to make it malfunction, but there are a few other things I want to throw in there, like showing a lot of error messages, so it seems fragile. But most of the core of it is covered by a core concept of information security, the CIA triad. Now, it's nothing to do with spies and gangsters. It's this set of concepts here of confidentiality, integrity, and availability. So robust software does not reveal information when it's not supposed to, alter information when it's not supposed to, or become unavailable when it's not supposed to, even when it's under attack by someone trying to force it to do so. So how do we achieve all that? Once again, we could bring in the experts, which in this case would be penetration testers, or pen testers for short. You can see why I couldn't resist using that image. The good news is you don't have to work for a huge company to use them. A lot of them work for independent computer security companies that you can hire on contract. However, they do tend to be rather expensive and highly disruptive because they need to test your production system. So once again, we'll usually have to do without their help, but we can get a long way by using their software. such as static analyzers that simulate the execution of our program, fuzzers, as I mentioned the fuzzing technique earlier, that tests our system's reaction to various kinds of invalid inputs, and probes that test our system's reaction to various known attacks. Many of these are available as open source. But even if management won't let us use such software, oh, no hacker tools here, we can still get a long way just by using their mindset. And the main part of that is to ask what could go wrong, whether accidentally or thanks to an attacker. And here the tone of voice is very important. It's not what could go wrong, as though we think nothing could. It's more statement-like, what could go wrong? I'm just trying to list it. I don't need a demonstration, thank you very much. And once we've brainstormed and run out of things that could go wrong for everything we've thought up, we should handle it. And yes, I know that's extremely vague, but how to handle something is going to vary enormously with exactly what it is. The upshot is that we should handle all reasonably foreseeable problems as gracefully as practical, from simple user error to system problems like a full disk, to even external problems like losing the network connection. Once we come up with some way to handle something, though, we need to test it because it's now an important part of our system. Our next aspect is one often seen as a trade-off with security: usability. If our software doesn't have this, then our users may stop using our software or recommending it out of sheer frustration. That could be disastrous for a software vendor or a software as a service company. And also, hard-to-use software can lead the user to do the wrong thing. It turns out that as of April 2024, at least 11 of the 82 people running for president of Iceland only meant to endorse some other candidate and only found out that they had started their campaign when somebody else endorsed them. Unfortunately, if we Google software usability, we mostly find stuff about letting people with various physical challenges use the software as well as the rest of us. In other words, accessibility, which is a good goal in itself, but it's just a subset. I'm adding on that it should be easy for everyone to use, not just equally difficult. To start defining it in a little more depth, it should be clear at all times what the user can do, should do, and must do, and what else the software can do, especially any help facilities, and all of that should be easy to do despite any challenges the user may be facing. We can start with the things that accessibility usually encompasses, like lack of vision or hearing or fine motor control. But there are others we need to be aware of as well. The user may lack literacy, at least in our character set. Like if I were trying to use some software with a user interface in, say, Arabic or something. They may be lacking certain cultural knowledge. We might not want to assume that everybody knows what the stoplight colors mean. They may even be of low intelligence. Yes, we may like to joke about stupid users, but statistically, half of them will be below average. Most of us do not work at Lake Wobegon. Another often overlooked part of usability is that all software should be usable, whether it's a web app, a mobile app, a desktop GUI app, or a command line app. Speaking to one of the few audiences that still does that. Or an API, whether it's through function calls like with a library or framework, or a wire protocol, whether binary or textual or whatever. So how do we achieve all that? Once again, ideally we can bring in the experts. And the bad news is, as I mentioned before, the people holding themselves forth as usability experts are mostly really accessibility experts, but the good news is we have a wide variety of other specialties we can get some help from. We mainly want a user experience expert. A user interface expert would get us almost as far, but even an old-fashioned print graphic designer has some training in basic visual design that will help us greatly in at least that aspect of usability. For the non-visual parts, this has been helped greatly by standards like REST and GraphQL and Swagger and so forth, and even by TDD, test-driven development, so you can figure out, oh, this API is kind of hard to use while we're writing the tests, haven't even written the code yet. So we can figure out, hey, maybe we should write it in a way that's a little more obvious and then make it so. However, as usual, we'll usually have to do without their help, and we can go a long way by applying some of their core principles. For instance, here we see an example of the KISS principle for keep it simple, stupid, or if you don't want to be so negative, some people say keep it super simple. Note the simple ease of use from these two companies with strong reputations for exactly that compared to the horrible, unusable mess from your company. I think a lot of us might recognize our own work in that, especially backenders like me. Another thing we can do, if the software is something that we can use ourselves, is to do so. In other words, eat our own dog food or dog food it. But remember, if we find our own software easy to use, that does not mean that the users will. We have inside knowledge that will help us a lot. But if there's anything we find difficult or unclear or whatever, it will be even worse for the users. So yes, dog food it, but mainly to find the pain points. And lastly, it may not be as definable or quantifiable as something like correctness, but a user interface can still be tested. We can bring in some of our typical users, even some that don't know our system yet, and have them try to accomplish basic tasks and watch them as they do it, which is what's going on in this picture. We can look for signs on their faces and their screens of frustration or confusion, or if we're lucky, at least contentment or happiness. Then ask them, was there anything they found unclear or difficult to do? Then fix their pain points, do more of the good parts, and lather, rinse, repeat. The next aspect is the one that we probably think of the most, maintainability. If our software doesn't have this, then changes are going to take longer, and we'll have a much higher probability of introducing bugs and developer headaches. I think we'd all probably agree that the basic concept is that maintainable software is easy to change. Thank you, Captain Obvious. Yeah, I think that's Captain Obvious back there in the third row. Yeah. But I'm going to add that it's easy to change with low probability of error. We don't want a dicey situation. And low fear of error, even for a novice programmer who is new to our project. That's a tall order. How do we do that? Well, for better or worse, the vast majority of software engineering advice is aimed squarely at this. So rather than expound on a lot of generic principles you've probably heard over and over, like single responsibility and good naming, high cohesion, loose coupling, blah, 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 I'm going to return to my theme and tell you how testing can help with maintainability. Some of you may already be in the habit of using tests as a sort of documentation of how your software, your API especially, should be used, especially if you're using Elixir, so you have doc tests available. A few other languages do, but seems like so far most don't. Also though, the tests that we wrote for any prior changes, whether it's a bug fix, a feature addition, whatever, form a regression test suite that will catch anything we break that used to work. And just knowing that that is there as a safety net will let us progress at a quick pace with a clear and open mind. I think I can, I think I can. Rather than creeping along slowly and erratically because we're terrified that we might break something and maybe not even notice until the users start complaining. And that speed up is why I even mentioned fear in the first place. There are also lots of tools we can use, like linters and complexity analyzers, and just cranking up the warnings on our compilers and interpreters and so forth. That will give us lots of hints how to improve our code, maybe even uncover some subtle bugs. In Elixir in particular, we have things like Credo and Dialyzer and so forth. For the final aspect, software should go easy on the resources. If we don't have this, our programs may run slowly, clog the network, make the user buy more resources like RAM and a faster CPU and so forth. They could even crash machines by running out of memory completely or disk space or whatever. Mainly we think of technical resources, especially the RAM and the CPU, to some extent bandwidth, and maybe even some people pay a bit of attention to screen space, one of my little pet peeves. But there are other sorts of resources we need to be aware of as well, like the user's patience and their brain power and the company's money, both the company that may be buying and running your software and the one that's paying you to develop it in the first place. So how do we achieve efficiency? Well, there are many kinds of resources and many ways to abuse most of them, so there are many kinds of inefficiency. But for the purpose of this discussion, I'll focus on the most common and obvious, which is slowness. I'm sure most of us have at some point had a program run slowly, and we'll stare at the code, find where we think it's inefficient, and spend a lot of time optimizing that, and run it again, and it's still slow. Turns out humans aren't very good at spotting the inefficiencies. So, to quote an earlier speaker, measure, measure, measure. I think that was you, Michal, right? Yes. On this very stage, if I remember rightly. So there are things like profilers and packet capture programs and so on that will tell us exactly where, or at least when, we're using too much RAM, CPU, bandwidth, etc., etc. Once we've found where it's slow, then comes the figuring out why it's slow. Certain kinds of programs tend to have certain problems in that regard, like distributed systems might be doing too much back and forth communication, or might be going over too slow of a network, or something using a database may have an inefficient model or an inefficient query, whatever. But most frequently, the problem is either something architectural, which is deeper than I want to get into right now, or a bad algorithm. Maybe we've got something with polynomial or exponential, maybe even factorial runtime. When looking at the problem from a slightly different angle would reveal a way to solve it in linear time, maybe even root or log or whatever, or the holy grail of constant time. Perhaps we're maybe using a bad data structure that's forcing us to use a bad algorithm, like we're appending to a list, one of the classic beginner errors in functional languages. And we should really be either prepending or using a tuple, maybe a tuple instead. So we need to be aware of the basic common data structures and algorithms, how to spot them in real-world problems and choose and change and combine them and analyze their demands on our assorted resources. And once it's fast enough, we can slap a performance test on it. You knew I had to mention testing eventually, right? In conclusion, if we developers remember to make sure that our software is appropriate, correct, robust, usable, maintainable, and efficient, then nobody should have any cause to be sour about the fruits of our labors. And now it's your turn. I'll take some questions. If you think of something later, there's my contact information, plus the URLs for my web page with more information about ACRUMEN and for the slides. So, any questions? Thank you.
All right, raise your hand if you have any questions. I do have one from the Hoover app. At what point in college could this be taught?
Oh, that's an interesting question. I hadn't thought about what point in college, or as Europeans more frequently say, university. I consider it to be aimed primarily at intermediate developers, because by then they've realized how important, yet fuzzy, software quality tends to be. Whereas, at least back in my day, the junior developers coming straight out of university were usually concerned almost exclusively with, does it work? If it runs and gives us the right answer when we poke at it with some typical data, fine. On the other end, seniors have often developed their own approach to quality, but I think they could still benefit from hearing about ACRUMEN so that they have a different point of view, and they might be struggling to put into words their approach to quality so as to teach it to any juniors and intermediates that they oversee. So in the context of the university, I would say probably later on in the curriculum rather than earlier. Definitely not the 101 level, perhaps junior year, maybe senior.
All right, thank you. Do we have more questions? Going once, going twice? No.
How would you evaluate quality as like tech debt? So for example, like if you're trying to release a feature, right, sometimes you can take a lot more tech debt to get it out of the way and then pay it off at a later point. Like how do you make that trade-off, or how do you negotiate that with management?
Okay. I have actually seen a couple of presentations on how one would measure tech debt. Unfortunately, I don't really remember much of the solid formulas and such that they used. I suppose one approach would be first make sure you've got decent test coverage to ensure your correctness. That's really the easiest to go after. Correctness is like the low-hanging fruit and what we're usually best at. And run mutation testing to make sure that your coverage actually means something, as opposed to just running the code and not asserting anything. Don't get me started on that. There are probably a few other things one could do to make some measurement of it falling short in the other aspects, such as bringing in users to try to accomplish tasks. Ask them perhaps to give the software a rating from 1 to 10 or whatever of how easy to use they found it to be. And that could also, come to think of it, affect the appropriateness. Does it do everything they need it to do? And are those features not overwhelmed by lots of other stuff they don't need? Is that enough of an answer? Thank you.
All right, one final question.
What tools do you use for mutation testing? I've never done that.
Okay. Well, in Elixir, there are a few. If I remember rightly, Darwin came out in the last few years, a little older, but I'm not sure if it's maintained anymore, is, why am I blanking on the name? I forget the name, but it's written by Devin Estes, who lives right here in Berlin. And there are, I think, maybe one or two more for Elixir and possibly Erlang and maybe other Beam languages. You can Google for my presentation on mutation testing, and actually the available tools is one of the last slides. And there was something else I was going to mention, but I forgot. Oh, yes. The main actual experience I have with mutation testing is more in the Ruby world rather than any of the Elixir and Erlang and other Beam languages. So the one I've actually used most would be Mutant, but that's not a Beam thing.
All right. Thank you once more.
Yeah. Thank you.